Let's get started. Homework 5 is out and it's due next Friday, same time. As a reminder, there won't be any homework due next Friday. So the 6th homework will be due the Friday of the week of the midterms. Sorry, not due, it will be handed out. I will hand out solutions to homework 4 at the end of the lecture. If I forget, please remind me. Reminder, there's a quiz on Monday. We'll start at 1 p.m. sharp, so try to come a bit early. And again, it's like true, false questions with justification. All right, any questions on logistics? All right, so let's kind of take stock of where we are. So we've kind of seen this whole process a couple of times. So just to remind you, you typically start out with a problem statement. This, in this case, was the resident matching program. Then you formally define the problem as a mathematical problem. You design an algorithm, typically start out with a brute force algorithm, and then kind of try to come up with something that's more efficient. You analyze the correctness of the algorithm, and then you try to analyze runtime, which means you need to design the data structures that you need to implement the various steps in your algorithm. So far, we spent the last few weeks talking about graphs, which are a great tool to go from a problem statement to an actual mathematical problem definition. It just turns out many of real-life problems, you are talking about relationships, and graphs are a great mathematical tool to model relationships. So for the rest of the course, we're going to focus more on kind of the actual design of algorithms. And we will consider 3 general techniques to design algorithms: the greedy algorithms, divide and conquer, and dynamic programming. It's not that there don't exist other techniques, it's just that we won't have time to cover anything more. So the first of these techniques is what's known as greedy algorithms. And I should kind of clarify, when I said there are 3 different techniques, it's not like, it's not like a formulaic thing that you feed in you don't have a procedure where if you feed in the problem statement, it'll automatically say, apply greedy, or apply divide and conquer, or apply dynamic programming. It's more of an art. So you have to figure out yourself as you design more and more algorithms, you get better at it. So you'll see the art part, and when I talk about greedy algorithms, I'll not define it formally. So at a high level, the idea in greedy algorithms is you build the final solution piece by piece. So it's always typically an iterative process. You kind of, instead of trying to build your final output in one go, you kind of try to build it step by step. So for example, if you had to output an array, instead of figuring out all values at once, you kind of maybe figure out the first value and then the second value and so on and so forth. And the reason it's called greedy is when you're trying to decide on the next piece of your solution, you are greedy or myopic. So you try to do what is the best at that point of time. So if you think about at least the part about the Gale-Shapley algorithm, where after a woman proposes to man, what does a man do? He does something greedy, right? So he tries to do what is the best he can get at that point of time, without worrying about whether that will create issues later on. And one of the things that doesn't quite fit into, the Gale-Shapley doesn't fit into this framework, but another common property of greedy algorithms is after you made this myopic decision, you never go back. Right, so it's kind of like, your algorithm is like Homer or someone. It's like it just has limited brain capacity. You just decide on something, and later on you just don't have the capacity to go back and change your decisions. As I said, this is not a formal definition, and it's kind of, it's more like the more of examples that you see, you'll try to recognize greedy algorithms more and more. And we're going to do quite a few examples so that that's kind of set. Having said that, people have indeed looked into formally defining greedy algorithms. And typically, of all the people that I know who have done research in this, it's like they've been teaching an undergraduate algorithms course like me, and they say, well, we don't have any formal definition of greedy algorithm. And so if you are an algorithm person, that's kind of an unsatisfactory thing. So I'll post a link to some of the papers that formally define greedy algorithms, and then you can do lots of interesting stuff, but to begin with, we are just not going to go down there, okay? Any questions so far? All right, so let's start off with an example problem. I apologize, kind of might be painful for you. It's the end of semester blues example. So this is last week of class for you guys, right? And you have 5 days in the week. And you have a bunch of stuff to do, right? So say you have a project that you knew was due on Friday, the first day of the semester, but as we all do, we just kept on not doing it, and now you have 5 days to finish it. Okay. There will be homework 10 due in 3:31. This is what I think you guys would be doing, but this is really what you guys will be doing, right? So this is what you'll be doing. And so on and so forth, right? So maybe you had to write a term paper, maybe you just want to party because the exams are coming up, or to study for exams, so on and so forth. So essentially what you have is a bunch of jobs or tasks that you know you have to do. For simplification, we're going to make two simplifying assumptions. The first is, once you decide on a job, you actually have fixed the start and the end time, which is not really true, right? I mean, even though you think the project might take 5 days, maybe you just don't have time and you use 3 days to do it. So you can try to compress things, but we're not going to, at least when we formalize this problem, we're not going to allow that, right? So we're going to assume that all the jobs that you have to do have a fixed start time and a fixed end time. The other thing that we're going to assume, at least at the beginning, and we'll revisit this later on in the course, is we're going to assume that all of these tasks have kind of the same profit or benefit to you, which is clearly not the case, right? So typically a project would be worth way more than 331 homeworks, and so you might not end up doing your 331 homework number 10, which is why I always tell you guys to keep your 3 drops towards the end, right? But, and the other thing, and this is not, I mean, you can again change this, but this is a reasonable assumption. You assume that at any point at any day, you can just do one job, right? And again, you can subdivide your day into smaller parts, and you can do all that kind of stuff, but let's just for simplicity assume my atomic unit of time is 1 day. And so the question is, what is the, given the restriction that you can only do one job in 1 day, and I tell you here all the jobs that you want to do, what is the maximum number that you can get done? Right? So you're trying to max, given that you have goofed off so far, you only have so much time to do, and what is the maximum that you can get out? And I said later on we're going to look at a version of this problem where each jobs have their own weight or profit margins, and then you do a weighted sum, right? So for example, what is the maximum total profit that I can get? But again, for now, let's just look at jobs are fixed, and they all give you the same amount of benefit. So you just want to maximize the number of jobs you can do. So the idea here is you basically greedily solve away your blues. And I mean, as I said, greedy algorithms are a wide class of problems. So just to kind of make the discussion a bit more directed, I'm going to tell you the class of problems I want to talk about. So the greediness will come from the following thing. You figure out some ordering of the tasks, right? So you order them from whatever, like first to last. And then what you do is you just kind of start from the first guy, pick that job. If it overlaps with any other job, just throw those guys away. Then go to the next remaining one, whatever it overlaps with, throw them away. And you just keep on doing this over and over again, okay? And so in that sense, the only thing that you have to kind of decide in an algorithm is how do you order the jobs. So once you do the ordering, the algorithm is kind of fixed. So maybe what you guys can do is talk with your friends for half a minute, try to think of various ways you can order these things of how to greedily pick jobs. Does the question make sense? Are there questions there? So the question is, try to figure out some heuristics or some ways of ordering jobs that you think would be good to solve this problem. Again, your goal, your goal is to do as many non-overlapping jobs as possible. And when you think of this heuristic, don't look at the specific example. Try to think of something that's kind of going to work in general.
So start with the largest, we're going to pick a project, and then we can't do any of the others. We start with the smallest, we're going to do an exam study, we're going to pick works, we're going to pick parties, we got 3, and then we'll go to 2.
All right, let's get back. Sorry, I forgot to mention one thing. In my mind, today we are finally starting the most interesting part of the course, which is actually designing algorithms. I mean, I know I've been going over basics so far. There are good reasons to do that. But things will get more interesting, and we're going to do a bunch of algorithms from now on. All right, how many of you have taken OS already? Okay, you guys are not going to answer my question, all right? All right, so those who have not taken OS, suggestions for how to order these things, that would be good. For paths, right? Yeah.
So you assign each task a priority based on the deadline and the amount of work required?
All right, so that path used the word priority, which is a good thing to say. I think instead of saying ordering, I think priority is the better. You assign priority to the jobs based on certain criteria, and then you do the things with highest priority first. So he said, use deadline and, sorry, what was the other thing he said?
The amount of work required.
The amount of work it requires. So maybe like a ratio of them or something, or?
Yeah.
Okay, so you could say, for example, you want to do stuff which have the earliest deadline first or latest deadline first?
So the amount of work required divided by deadline.
Okay, so part suggestion is amount of work required divided by deadline. The intuition being, or maybe you want to do the reverse, I don't know, but the intuition is larger jobs should have lower priority, and those who have the earlier deadlines should get more priority, and so you want to combine them in such a way that it turns out to the right thing. Ratio works, I'm just confused which should be on numerator and denominator, but one of them would do what you want to do. Okay, good. Any other suggestions? Tyler?
I have a question. What is the longest job is the earliest deadline?
Sorry?
What is the longest job is the earliest deadline?
What do you mean, Raj? Oh, you mean the longest job has the earliest finish time. That can happen. So, okay, I should have mentioned, as we've been doing in pretty much all of these algorithms, once I specified, in this case, start time and end time, other than that, there are no other restrictions. So your algorithm has to handle all possible weirdo cases and non-weirdo cases at the same time. Any other suggestions? All right, those of you taken OS, suggestions? I know you know the answer. Okay. Hopefully when we get to the actual algorithm, you'll remember. All right, so I'm going to look at few suggestions, some of which include what Path said and some which kind of make sense, but no one says, but I'm still going to suggest it. So first thing you could try to do is order by start time, right? So you are kind of getting nervous, you just want to get started, right? So whichever starts first, let's just do that. And if you look at this example, it turns out that that's bad, right? So in this case, term paper and project both start on the first day. And let's say you pick, I think in this case, so let's say you have to break ties somehow. Let's assume I do project first. It actually turns out for the argument doesn't matter whichever one you do first. So let's say I run this through this order. So I pick project. Now the issue is once you take project, you cannot do anything else, right? Everything overlaps with project. So if I do project, I can just schedule one guy, which is project. But that's clearly not the best we can do. So in this case, the algorithm will schedule one job. Whereas if you had picked exam, party, and 331, I definitely put 331 on purpose, you can do 3. And it turns out this is the best possible you can do. You can schedule up to 3 jobs. So just by one simple example, you have to rule out start time as your ordering. All right, so the other thing is kind of related to what Parth said is let's just do duration, right? So you want to somehow say that jobs that have large durations should get lower priority, like shorter jobs should get higher priority. So I'll give you a different example. Let's say you have 3 jobs. The green and the purple are really, really long, right? And you have this short red guy. So red guy is your shortest job, the other 2s are much bigger. And now if you go by duration, the ordering is you have to do red first, right? But again, if you pick red, you're throwing away the other 2 guys because both overlap, right? So in this case, if you do by duration, the algorithm will say you can schedule 1, but the better thing is not to schedule the red guy. And it turns out there's another thing you can do, which is one of the common themes that's coming up from these examples is perhaps jobs that overlap with lot are not good jobs to schedule, right? At least in the 2 examples that we saw, that was the case. So you could, for example, try to schedule jobs that have the least number of conflicts first. Unfortunately, even that doesn't work. And so you can show that doesn't. So finally, this is related to Parth's thing, but the interesting thing is you actually ignore duration altogether. So those of you who did OS, it's like the earliest deadline first algorithm that you hopefully saw some point of time. So the point is let's just order by the end time. Right? So the jobs that finish earliest get scheduled first. So in this case, the first guy that finishes his exam, so I'm sorry, these colors are not that great, but you go exam and then you have to break ties between term paper and party. So let's say term paper comes first, and then party, and then project, and then 331. Right, so let's see what happens in this order. So I pick exam study first. Now if I pick exam, I cannot schedule term paper or project, so I have to kind of throw them away. So I throw away project, I throw away term paper. The next guy among the remaining guys that finishes earliest is party, so you party, and then you do 331. And so at least in this case, you get the best possible schedule. Okay. And so it turns out that this actually works, right? And so we could argue or prove today, or we'll start proving today, or more likely on Monday, that this is an optimal algorithm, right? So if you order by earliest finish time and make sure you don't schedule overlapping jobs, that this is provably the best thing you can do. Now, if you think about it, this kind of sounds fishy, right? Because, I mean, Parth's suggestion is great. Like, why shouldn't you include duration, right? I mean, why does ignoring the duration or even the start time work, right? I mean, a priori, there's no reason to believe that the algorithm where you order by start time fails, but ordering by finish time actually works, because in both cases, you're ignoring some part of the input, right? And it works. So if you sit down and think about it and try to prove it yourself, it's not obvious why this would work. And this, I think, is the first example of an algorithm that I think is seen in the course where the proof of correctness might not be that obvious, at least intuitively. Right? So all the algorithms that we've seen so far, you might have to work a bit to kind of formally prove it, but like in Gale-Shapley and things like that, they seem like it's on the right track. Right? Okay, any questions? All right, so what we're going to do today is argue the correctness of this greedy algorithm. But before we do that, we're also going to formally define the problem. Let's make sure everyone's on the same page and so on and so forth. Are there any questions before I start? No? All right. So this problem is in literature known as the interval scheduling problem. The reason it's called interval is because I said all the jobs have a fixed start time and a fixed end time. So if you kind of draw, as if you're drawing kind of that bar stuff on the slide, this is like an interval start time and an end time. Okay. And so the input to the problem are n intervals. And the ith interval has a fixed start time and we'll denote this by S of I, S for start, and then you have a finish time, denote as F of I. And we have a convention. Whenever somebody tells you that they have a range, one of the things you should first ask is whether the endpoints are included or not. Right? So there are kind of 4 possible combinations depending on whether you start from the start point or one after that, or whether you end at the finish point or one before that. So the convention that we're going to do is the ith interval, we're going to assume starts from Si but finishes just starts from Si but finishes just before Fi. Okay? So in math this is closed and this is open, and this is same as saying you start out from Si and go up to Fi minus 1. Right? So for example, if I have 1, 4, this is my set 1, 2, 3. Right, so this is my convention. Why did I choose it? I actually at this point forgot, but that's how I've been doing it, so that's how we'll do it. It really doesn't matter. I mean, if you wanted, you can make it finish exactly at Fi. The algorithms that we're going to consider won't to. But for our discussion, we're going to assume it starts at Si, but actually has to finish by Fi minus 1. All right, so this is my input. And my output is a valid schedule with maximum number of intervals in it. Okay? Now I've not defined what a schedule is, what a valid schedule is, so let's do that. So a schedule is just a subset of jobs that you're picking. And typically when you think of schedule, you want it without any conflicts and stuff, but in this definition, mathematically what I'm defining, schedule, you have conflicts. A valid schedule is one that has no conflicts. So schedule S is valid if it has no conflicts. And now I have to define conflicts for you, so that's the last definition. So we say two intervals I and j are, two intervals I and j conflict if they overlap. Okay? So if you draw them out, they overlap. So pictorially, it will look something like I'll have 4 cases. Okay. And it's either the case that J is completely contained within I. So again, this is my start time corresponding to this. This is my finish time corresponding to this. Or I is completely contained within J. Or I overlaps J from the left. Or I overlaps J from the right. Okay. So these are the only 4 ways you can have 2 intervals if you draw them on the real line that they can conflict. All right, any questions so far? All right, so again, just some quick data structure issues. One question is, how do you determine how is the input represented? And I really don't care. It can be an array of pairs of Si, Fi, or you could have 2 arrays where the ith thing is the ith guy in one array is the start time, the ith entry in the other is the finish time. Right? Basically, you need some reasonable way of having a list or array of these pairs of Si and Fi. Okay? So let's say they are in arrays. So given I, you can immediately recover the start and the finish times. So my question to you is, if I give you I and J, how quickly can you decide if I and J conflict? Is the question clear? Let's say I have an array of these pairs of Si and Fi, and I give you 2 intervals, and this is I and J, and I want you to tell me how much time it will take for, or what is the quickest you can tell whether they conflict or not. Talk to your friends for half a minute, let me know if you have any questions. If not, what would be an answer for this? All right, any questions first? Okay, if not, how much time would it take you to, if I give you a, Tyler? OFN is correct, but you can do better. But constant time. Why would it constant time?
You can just look at the I position and check whether J is something or
Right, so kind of to paraphrase what Pat said, essentially what you need to do whether I and J conflict is you check whether one of these 4 cases occur. Right? Now if you look at all of these 4 cases, you can completely figure it out by knowing the start and finish time of both. Right? So you just look at them and there's certain Boolean conditions you need to satisfy. But the point is, it's just some Boolean condition with 4 variables. Right? So you can do it in constant time. So you can check each of these, whether each of these cases hold in constant time. And since you have only 4 checks to do, you can do the entire thing in constant time. Okay? All right, so this is order 1, and the basic idea is check if one of the 4 cases above hold. And as I said, each check can be done in constant time. Okay. All right, good. So given 2 intervals, I can do this check quickly. All right, so something to keep in mind which would be useful as we go on. I'll write down the algorithm formally in a bit, but before we do that, I'm going to make one simplifying assumption that kind of makes the notation simpler as we go along. And that starts off with that observation is, if you have a valid schedule, okay, what, again, valid means that there are no overlaps. So if you kind of draw them out, none of them overlap. So you can just, they kind of disjoint in time, and they're just following one after the other. And if you have something like this, notice that it doesn't matter if you sort them by the start time or sort them by the finish time. You're going to get back exactly the same order. So a valid schedule sorted by start time or finish time has the same order. And the way we're going to use this is just, we're just going to say, we'll assume that the input that's given to us is actually sorted by finish times, like all the inputs to the problem, which is not necessarily a valid schedule. Okay? So we're going to assume the input intervals are sorted by finish time. So what that means is F1 is no bigger than F2, is no bigger than F3, and no bigger than F1. Makes sense? So I'm just sorting by finish time. Okay. Any questions? Okay, then I have a question for you guys. So let's say this is true. You are given the input sorted by the finish time. What is the index of the job that would be scheduled by the greedy algorithm first? Or what is one valid job that it can schedule? I'm sorry, I forgot your name. Brian. Sorry? First one, right? Because you again, remember the greedy algorithm is you're going to sort, or you're going to order them by the finish time, and the one with the earliest finish time goes first. So by definition, if all these finish times are sorted in increasing order, F1 by definition has the earliest finish time. Right? Now it is possible two could also have the same finish time, but for sure one will have the earliest finish time. And so without loss of generality, we can assume that the greedy algorithm will always schedule the first guy. All right. So let's look at the algorithm. Let's make sure that still remains. Okay, good. So here's our greedy algorithm to solve this problem. I'm going to have this set R, which at any point of the run of the algorithm is kind of the intervals that we have not dealt with yet. And so to begin with, I have not dealt with any. And again, remember, n is the set of all numbers from 1 to n. Similarly, S would be my empty set. This is going to be the guys that I have put in my schedule. And at the end of the algorithm, whatever is in this set S is what I'm going to output. And so basically, what the algorithm does is, as long as there is some interval that you have not dealt with, you run this loop. And so again, now you're going to use the fact that the intervals are sorted by their finish time. Let I be the smallest index of any job in R, that is the, again, by definition, if this is the smallest index, what this is saying is, among all the jobs that remain, pick the one with the earliest finish time. Once I have this I, I'll add I to my final set. I should delete I from R because I've put it in, so I've definitely handled this. And not only that, I should actually delete every guy that overlaps with I also. Okay? So delete all j in R that conflict with I. And then finally, once this loop is done, you return whatever set S was. And we're just going to call it S star so that, I mean, we are making it clear that this is the final schedule that the algorithm wants. Okay? So this is the final kind of essentially the pseudocode of the greedy algorithm that we want to solve the interval scheduling problem. Any questions on the problem definition of the greedy algorithm? Okay. So there are a couple of simple things to note. So the first thing to note is the output of the algorithm is always a valid schedule, right? Because whenever we are adding a job I to S, we are removing everything that conflicts with it. So in the future, if I have put I in my schedule, I'm not going to put in any jobs that conflict with it. And so at the very least, I'm making sure that there are no conflicts in my output. So it is by definition a valid schedule. But we want to prove something stronger, right? We want to argue that this is the best possible output. So in other words, we want to argue the output of this greedy algorithm has the maximum number of intervals that you could pack in any valid schedule. Okay? So we're going to argue the correctness. And so the theorem that we want to argue is S star is an optimal valid schedule, that is, it has the maximum number of possible intervals maximum number of intervals in all possible valid schedules. Okay. So any questions on what we want to prove? Kishan? Smallest? Oh, so Kishan's question is, how do I figure out the smallest I in this set R? So remember, every interval is indexed by an index, right? A number from 1 to n. So in set R, you'll have some subset of these numbers. Just pick the minimum number. Or are you asking how are you going to do it quickly?
No, like, is it based on the start time?
So the question is it based on start time? No, it's based on the finish time. Remember, we are assuming everything's sorted by the finish time. So if the intervals are already sorted by the finish time, the smallest I will have the smallest finish time. Any other questions? Lloyd.
Is it possible to lose a job at 2.4?
So question is it possible to lose a job? So are asking, would it be the case that you actually throw away some jobs in 2.4? Yes, and in fact that is crucial. If you don't do that, your algorithm will be wrong.
Can you get them back?
Questions can get them back now. So the point is, you can never have two guys that overlap. So if you, in any algorithm, if you pick one interval, you necessarily have to throw away everything that overlaps with it. Okay. So once you make the decision, and so again, this is like the greedy algorithm, right? I made my decision to put an I. Once I made the decision, my hands are tied. Everything that conflicts has to be thrown away. Any other questions? All right, so we want to argue this. And even before I go into how you might even try to prove such a thing, I'll make two simple observations which I'll let you guys prove at home as exercises. So the first one is to argue that the algorithm terminates Because, well, if the algorithm doesn't terminate, you can't prove jack, right? So, I mean, you have no S star. So you have to prove that it terminates. And the basic idea, of course, is the reason it will terminate is every time you have a loop, you're going to throw away at least one guy out, right? Because you're picking the guy with the earliest finish time in R, and at the very least throwing that guy out. So every time loop runs, the size of R shrinks by 1. And so it can shrink at most n times because that's the number of intervals you had to begin with. Right? So this way you can argue that the algorithm terminates. The second one is what I had mentioned earlier, which is S star is a valid schedule. And this comes back to Lloyd's question. The reason it's a valid schedule is because in step 3.4, you're making sure that the moment I put in I in my output S, I'm just going to throw away everything that conflicts with it. Okay? So just that greedy step by itself will ensure that your final output will not have anything that conflicts with anything else. Okay? But note that by itself, arguing that S star is a valid schedule doesn't give you anything, right? So the empty set is also a valid schedule because there's nothing in there to conflict with each other. But that clearly is not the best thing that's possible. So what we have to argue now is, okay, it's a valid schedule, but now we have to argue that it indeed has a maximum number of intervals in there. Okay. So before I go into proving this, just a quick digression. And so this, we'll see, will turn up fairly often in all the greedy algorithms that we're going to look at. You're always trying to come up with the quote unquote the best possible solution. So with a certain goal. In this case, it's how many intervals can you schedule? And so the question is, how do you go about arguing this? And so it turns out, again, it's kind of not a formulaic way, but as a rule of thumb, there are kind of two ways of proving correctness of greedy algorithm that works. And we're going to see multiple examples of both. Okay? So we want to prove correctness of greedy algorithms, and they have names. So the first one says greedy stays ahead, and this is what we're going to use for the interval scheduling problem. At a high level, the idea is your greedy algorithm is making decisions one by one, right? So you're adding this this job I in each iteration of the algorithm. And you somehow want to argue that if I just look at the solutions so far, like all the guys that I've picked, at any point at the end of iteration of the algorithm, in some very strict, concrete sense, you're always doing better than the optimal at that point. So what you want to argue is at the end, you're doing as well as the optimal. But the way you argue it is actually at each step, you're doing better. Okay. The other one is known as the exchange argument. And I'm going to talk more about this later because it will make more sense later on. All right, so we want to prove this theorem which says S star is an optimal solution, or it's a maximum number of guys. But how do you go about proving this, right? You can't say that, well, let's assume the output of greedy is optimal because, well, that's what you're trying to prove. And this is where you have to start doing some kind of mental gymnastics. And so the way we're going to argue is the following. We're going to say, let's say by magic someone hands you one possible optimal solution. So someone gives you an optimal solution that has a maximum number of intervals in there. Then by just using the fact that it is an optimal solution to the problem. So the only thing I'm going to assume about this magic guy is that A, it's a valid schedule, and B, it has a maximum number of possible intervals in it. Just using these two properties and the definition of the algorithm, we're going to argue that the greedy output is just as good as that one. Okay. So let's try to make it a bit more precise. So let the script O for optimal be an optimal solution. And it's crucial that I say it's and because it's easy to come up with examples where there's more than one possible such solution. So again, what I mean by optimal is among all possible valid schedules, if we look at the size of the schedule, which again, remember, it's a set of jobs, so the size of the set is the number of intervals in it, is the maximum possible. Okay? Another fun exercise for you to think about is convince yourself that such an optimal always exists. Okay? Again, intuitively it makes sense, right? So you know there always exists some solution, and then if you list all possible solutions, you just look at their sizes, and since you have a bunch of finite number of such schedules, each one of them which will give a number which is its size, so you have finite number of such sizes, by definition there had to exist one which is maximum. Okay? Formally proving that might be a pain, but intuitively, hopefully that's clear. Okay. So once I have this in place, so one sufficient way to argue this is to just argue that the output of the greedy algorithm actually just happens to be this optimal solution. Right? If this were true, you're done, because by definition, my script O was an optimal solution. So if I get lucky and this happens, then I'm good. But do any of you see what's the issue with this? Why this cannot work as an argument? Okay, so the reason it won't work is this an optimal solution, right? So all I have assumed so far is script O is an optimal solution, and there could be multiple optimal solutions for one given instance, right? So you could have two sets that are different, two schedules that are different, but have the same number of largest possible number of intervals, right? So the issue again here is the problem is you could have multiple optimal solutions. So for example, here is an instance for n equal to 2, where you can only have one guy in your optimal solution because both of them conflict. This, for example, would be S star because that's the guy that finishes first. But since the only thing you know about the optimal solution is that it's optimal, it might as well be this other guy, right? So you cannot prove, I mean, this is just a counterexample to the effort of trying to prove that S star is actually equal to O. But again, the point is, we only care whether S star is optimal. If there's more than one, I don't care by the problem definition whether my algorithm outputs this or this, as long as it outputs one of them. Right? And so the second idea, which is what we are going to pursue, is to argue that, fine, it might not be exactly this optimal solution, but I'll argue that the number of intervals in my output is same as the optimal. And note that that's enough. Right? Because why? By definition, O has a maximum number of possible intervals that you can add in a valid schedule. And if I prove this, that the size of S star is exactly equal to the number of intervals in O, by definition of O, I'm done. So instead of proving theorem 1, which was kind of a bunch of lines in English, we're going to just prove this nice, simple, short theorem which says we're going to argue that the sizes of these two are the same. Okay. So let me, in the remaining time that I have, stress on one crucial thing, and this is very important. Okay? The only thing I can assume about O is that it's an optimal solution. So what that means is A, it's a valid solution, and B, it has a maximum number of possible schedules. But I cannot assume anything beyond that. Nothing about, maybe I use this kind of algorithmic convolution. Oh, no, nothing. Right? only what's implied by the algorithm, okay? So only things you can assume about the optimal solution is one, it's a valid schedule, and two, it is optimal. Okay? And most importantly, nothing else. Okay? I mean, when I say nothing else, I mean nothing else about, oh, we of course have to use properties of a greedy algorithm to come up with this. But this is a crucial thing, and this is a topic, an observation or comment that I want you guys to think really, really deeply about, because we're going to make use of this over and over and over again in this course, okay? I have solutions to homework 4.